to introduce our resource person.
A very good morning to everyone. On behalf of Department of Electronics and Communication Engineering, Mahindra Engineering College, I am Sweepin Sonia, Assistant Professor of Department of ECE, take this opportunity to welcome our resource person and all the participants to the session 5 of 5-day FDP on the topic MIMO Metamaterial Inspired Antennas. And today we have privilege to have with us expert from the field of education who shall be reflecting on the topic of the session. Dr.R.Pandeeswari is currently working as an Associate Professor of Department of ECE, NIT Trichy. She obtained her BE in Electronics and Communication Engineering from Manonmaniam Sundarnar University, ME in Applied Electronics from Madurai Kamaraj University, and received her PhD from National Institute of Technology, Tiruchirappalli. Her research work investigates metamaterial-inspired techniques for antenna performance enhancement. Her areas of interest include metamaterials, antennas, bioimplantable antennas, electromagnetics, microwave engineering, waveguides, reconfigurable antennas for cognitive radio applications. Her research area mainly focused on planar antennas, electromagnetic metamaterials, and metamaterial-inspired antennas. Earlier, she has teaching experience in Mohammed Sadar College of Engineering, PMR Institute of Technology, Chennai, and KLN College of Information Technology, Madurai. She has authored 16 papers in reputed journals and published her research papers in proceedings of 25 international conferences. Also, she has presented her work in 3 international conferences held at Russia, Singapore, and Malaysia. She won the Best Paper Award in ICICI 2017 IEEE conference held at Coimbatore. She received a financial grant of Rs 48 lakh for the project titled Metamaterial Based Low Profile LTCC Balanced Antipodal Vivaldi Antenna for 5G Enhanced Mobile Broadband with University of Saskatchewan, Canada. With this short note, I would like to call upon a resource person, Dr.R.Pandeeswari, to enlighten us with your words. Ma'am.
Yes. Good morning to all. First of all, my best wishes and congratulations to organizer of this program, FDP on Artificial Intelligence Enabled Sensors and Network for 5G Wireless Communication. Thanks for this opportunity. Previous speaker nicely talked about artificial intelligence for beginners. I also attended. He told many interesting things. I'm going to concentrate on MIMO metamaterial inspired antennas. First of all, we should understand what are the frequency range assigned for IoT and 5G application. Then we should know, you should know what is metamaterial, what are the properties of metamaterial. Then what is metamaterial inspired antenna? What about the design of metamaterial inspired antennas? Then we will move to metamaterial inspired MIMO antennas. So let me start from this IoT, and this is outline of my presentation. So we all know very well IoT and 5G application both are very it's a booming market. We all moving towards IoT applications and 5G applications. Is it audible, Dr. Ponlada?
Yes, ma'am, it's audible.
Yes. Thank you. So we should know what is the frequency range of IoT and 5G. So here you can see IoT protocols mostly use ISM band of frequencies, that is from 4.33 gigahertz and 915 megahertz, and also from another frequency range 2.4 gigahertz to 5 gigahertz. See, for 5G, we should know what are the requirements for 5G antennas. Actually, 5G antennas should provide high gain and also stable radiation pattern and broad bandwidth. So these are the requirements of 5G antenna. Not only these things, in addition to that, size should be very, very small, very, very compact size. If you consider frequency range for 5G, actually that is coming in two different things. One is FR1 and another one is FR2. if you consider FR1, see, this ranges from 450 megahertz to 6 gigahertz. So nowadays, people are talking about 6 gigahertz, sub 6 gigahertz band. No, so this also includes LTE frequency range. Another frequency range, that is millimeter wave, that is from 24.25 to 52.6 gigahertz. So this is the frequency range assigned for 5G applications. Next, see here, what are the important parameters we have to consider while designing antenna for IoT applications or 5G application? So first one is shape. What about the shape and size of the antenna? Then mounting option, then frequency of operation, then coverage requirement, then omnidirectional radiation pattern, then cost of the antenna, gain of the antenna. So before designing antenna for IoT or 5G application, so we have to we have to consider these things in our design. So next, let me introduce what is metamaterial. What are the properties of metamaterial? Actually, metamaterial, see, from this word itself, you can understand. See, meta means something unusual, something not available in nature. So this is not a natural material. This is an artificial material, right? This is an artificial material. Even you can say artificial engineered structure designed to display some unusual properties. So that's why this material name is known as meta material. Here material means, the word material here is, see, it can also display properties similar to material. That's why this particular material is known as meta material. Actually, this was introduced by Russian scientists. That was in the year 1968. This is the first paper on metamaterial. You can see the title of the paper. I have highlighted that paper. See, electrodynamics of substances with simultaneously negative value of mu and epsilon. So from this paper title itself, you can understand this is the material having simultaneously negative value of mu and epsilon, mu permeability and permittivity. So both parameters are negative, mu and epsilon. Permeability also negative, permittivity also negative. That's why this material is known as metamaterial. See, you can we can say negative mu in some of the natural material. Negative epsilon also we can find in some of the natural material, but none of the material having simultaneously negative value of mu and epsilon. That's why this material is known as metamaterial. So using this material, we can design miniature MIC components, microwave components, microwave antennas, microwave filters. So this is very, very useful for microwave application. Then we have to understand this classification, that is classification of material based on mu and epsilon. Actually, I have taken this content from Callow's textbook, one textbook, popular textbook available for this metamaterial. So I have taken from that textbook only. So this is classification of material based on mu and epsilon. You can see here 4 quadrants are there. One is first ones. See, first one you can see both are positive in first quadrant. So that material is conventional material. So this is known as double positive material. So for conventional material, we all know very well refractive index is positive. It supports forward wave propagation. So this is the this is the nature of our conventional material. If you consider third quadrant, actually metamaterial coming in third quadrant only. So in third quadrant, you can see mu, epsilon less than 0, mu also less than 0. So permeability, permittivity, both are negative, right? So due to negative value of epsilon and mu, refractive index is positive. So refractive index is positive means phase constant also negative. what about refractive index not positive? Refractive index is negative for metamaterial, right? So you should understand this clearly. Refractive index is negative for metamaterial, whereas refractive index is positive for our conventional material. So due to this nature of material, it supports backward wave propagation. So this is main differences between conventional material, that is double positive material, and double negative meta material, right? If you consider second quadrant and third quadrant, you can see only one parameter is negative, either one is negative. So we can say SNG material, single negative mu negative material, or single negative epsilon negative material. Actually, for SNG, ENG material, SNG, MNG material, there is no wave propagation. That is evanescent wave propagation. So this is classification of material based on mu and epsilon. So here our metamaterial coming in third quadrant. So it is having negative value of mu and epsilon. Next, I would like to list out what are the properties of metamaterial. What are the unique properties of metamaterial? Already I mentioned, this is used to provide simultaneously negative value of permeability and permittivity over a certain range of microwave frequency. Refractive index is negative. Phase constant also negative. So wave number, if you find the wave number, that is also going to be negative. And phase velocity, BP, also negative. But if you consider group velocity, that is positive, right? So it is having anti-parallel phase and group velocity, right? So here beta negative, no, actually phase constant determines the direction of wave propagation, no. So due to negative value of beta, it supports backward wave propagation. So these are some unusual, some unique properties of metamaterial. Next, this slide shows what are the basic metamaterial elements. Already I mentioned, actually metamaterial is artificial engineered structure, right? So by using some special kind of structure, we can we can extract these properties. So here I would like to introduce what are all the different metamaterial structures. So you can see one is splittering resonator. So this is known as SNG MNG material, single negative mu negative material. Whereas thin wire, this is SNG ENG material, single negative epsilon negative material. So for DNG material, you have to combine SRR, SNG ENG and SNG MNG material. Then only we can we can synthesize DNG material, right? So double negative meta material. CSRR, this is complementary splittering resonator. So this is used to provide negative permittivity. So here you are able to see, here I have included the splittering resonator structure. So this is the structure. This is used to provide SNG MNG property, that is negative value of permeability, right? So this is equivalent circuit of splittering resonator. Next one is array of thin wire structure, right? Array of thin wire structure. This is used to provide negative permittivity. Mostly we will be using splittering resonator or complementary splittering resonator for our metamaterial inspired antennas, right? SRR and CSRR, complementary splittering resonator. So this is equivalent circuit of splittering resonator. See, equivalent circuit is very, very useful to determine the resonant frequency of this splittering resonator structure. That's why here I have included here this equivalent circuit. Here you can see L and C combination. See, you can replace entire metal ring by this inductance, and gap, the split gap by this capacitance. And also you can see there is a gap between outer and inner ring. So you can replace that gap by capacitance. And also you can replace mutual coupling between inner and outer ring by this mutual CM, this capacitor, right? So here SRR, splittering resonator, consists of two metallic rings, right? Two concentric metallic ring. There is a split you can see, split is placed on opposite side of the ring. One split is placed on this side, another split is placed on opposite side. So this kind of structure is known as split ring resonator structure. So using this structure, you can get SNG, MNG property, right? See, for single ring resonator, this is equivalent circuit, LCR. See, if the distance between outer and inner ring, if it is very, very small, then you can replace double ring resonator by single ring resonator. So this is equivalent circuit of SRR. So this is array of SRR and array of thin wire structures. So you can arrange these things in array like this, right? 1D or 2D. Then you can extract that material property. So first one is negative epsilon, positive mu structure, whereas second one is positive epsilon. Permittivity, that is going to be positive, but permeability is negative. So this is array of thin wire and array of split ring resonator structure. So here this combination array of split ring resonator and thin wire, this is combined to produce DNG material, right? So for DNG material, you have to combine SNG, ENG and SNG, MNG material, then only we can get DNG material. So first one is 1D MTM. Second one is this is arranged in both direction, 2D MTM, two-dimensional meta material structure, MTM structure, right? So next here you can see this meta materials are represented by anisotropic uniaxial permeability and permittivity tensors, right? So you can see epsilon XX, YY, ZZ, that is not equal to 0, but other cross tensors are equal to 0. X, Y, Y, Z and are 0. Similarly, mu also, this is represented by this kind of tensors, right? So metamaterials generally represented by this kind of tensors. Next, we will see what are the different terminologies assigned to metamaterial. See, some papers, some authors used the Veselago medium, some authors used the DNG medium. So some papers you can find this word also, negative refractive index medium. Actually, refractive index is negative, no? So some authors introduced this also, negative refractive index medium, right? Even you can see, you can also call this material as negative phase velocity medium due to this property, that is phase velocity negative, no? So that's why we can also call this as negative phase velocity medium. And we can also even, you can call this as backward wave medium, right? Due to backward wave propagation, we can also call this material as backward wave medium, right? Next, another interesting thing. See, this is transmission line model of metamaterial. See, for conventional transmission line, we know what about the equivalent circuit. We studied in transmission line theory, no? See, for a lossy transmission line and lossless transmission line. See, for lossless transmission line means R and G will not be there. Only you will be having what we are having L and C, no? So for conventional lossless transmission line, inductor is placed in series arm, whereas capacitor is placed in shunt arm. Actually, metamaterial transmission line is nothing but dual of conventional transmission line. So we all know very well what is dual network, what are dual elements, how to draw the dual network, that and all we have studied in what network theory, no? So using same concept, duality concept, you can replace inductor by capacitor and capacitor by inductor, right? So this is a transmission line model of metamaterial. So this is derived by using duality concept. Also, this is also derived from a very old concept, that is a backward wave propagation, right? Actually, backward wave concept, that is not a new concept, that is very, very old concept that was introduced in 1940 itself. Actually, 1940 itself, that concept was introduced. Actually, this kind of transmission line model, it can provide, it can support backward wave propagation. So this metamaterial model also derived from that concept only. Actually, metamaterial can also support backward wave propagation, no? So using that concept, this transmission line model of metamaterial is derived. So you can see capacitor, this is in series arm, whereas inductor, this is in shunt arm. See, for if you derive properties of this transmission line model of metamaterial, then we will be getting properties. What are all the properties we discussed earlier? Same thing here also. We are getting by deriving all these things for this transmission line model. See, gamma, see this propagation constant, this is, you can see, this is equal to J beta, that is phase constant, this is negative, beta, phase constant is negative, right? Bp also negative, Bg also positive. Already I told you, phase constant negative, Bp negative, Bg positive. It is having anti-parallel phase and group velocity, right? Same thing we are getting by using transmission line model of metamaterial, right? So this is composite right left-handed transmission line. That is nothing but a combination of what a conventional transmission line and a metamaterial transmission line. You can see LRCL. Actually, LRCR, that is representing conventional transmission line, elements of conventional transmission line, where CLLL, that is nothing but metamaterial elements, right? So this is combination of both composite right left-handed transmission line. Next slide, let me introduce what is why here subscript R for conventional transmission line, why here the subscript L for metamaterial. So here you can see this is vector representation of conventional material and metamaterial. First one is for conventional material, right? You can see if you consider three vectors: electric field vector, magnetic field vector, and beta phase constant vector. If you consider these three vectors for conventional material, then it is represented by right-handed triples, right? These three vectors forms right-handed triple. That's why your word right-handed material for conventional material. Also, pointing vector that also lies in the direction of what phase constant, right? Second one is vector representation for metamaterial. See here, it is represented by left-handed triple, opposite, that is anti-clockwise direction. You can see beta, this is positive, right? So these three vectors form left-handed triples. That's why here the word right-handed material and left-handed material. This is the reason behind the term left-handed and right-handed material. So you can also call metamaterial as left-handed material, right? So this is vector representation of conventional material and metamaterial. Here we will try to summarize what are the properties of right-handed, that is our conventional medium, and metamaterial, that is left-handed medium. See, for right-handed medium, Bp greater than 0, beta greater than 0, Vg greater than 0. If you consider metamaterial left-handed medium, Bp less than 0, beta less than 0, Vg also greater than 0. So this is very, very interesting fact about metamaterial. Next, another interesting thing is boundary conditions. About metamaterial. See, for conventional material, see, we know very well tangential component and normal component of that boundary condition, normal component of electric field and magnetic field, tangential component of electric field and magnetic field. Actually, that is continuous at the interface between two medium. So that is what we know about conventional medium, right? See, if you consider tangential component, actually tangential component that don't depend on material property. That's why here there is no change in tangential component of electric field and magnetic field at the interface between two medium. See, first medium is right-handed medium and second medium is left-handed medium. But if you consider normal component depends on what are that material properties, epsilon and mu. That's why here there is a change in normal component of magnetic field and electric field. So this is another interesting fact about metamaterial. So this is boundary conditions at the interface between a right-handed medium and left-handed medium. So there is no change in tangential component of electric field and magnetic field, but you can see there is change in normal component of electric field and magnetic field due to these material properties. And also we all know very well Snell's law. Actually, we know what is Snell's law of reflection and Snell's law of refraction. Actually, there's a change in Snell's law of refraction due to this material properties. But if you consider reflection, there is no change in reflection. Actually, reflection is related to same medium, no? So that's why there is no change in reflection. But here there is a change in Snell's law of refraction due to this material property. You can see this is what happening in conventional medium for incident wave and transmitted wave and reflected wave. So this is for conventional medium, right? So this is first one is Snell's law of refraction for conventional medium. Both are right-handed, that is positive DPS medium. But if you consider a second figure, first medium is right-handed, second medium is left-handed medium. That's why here you can see here instead of going in positive direction, it travels in opposite direction. This is also due to negative value of this wave number, this wave vector, and also that refractive index. So here this is also another interesting thing about metamaterial. And also this is also one of the interesting fact about metamaterial. See, we know what about the focusing nature of convex and concave lens. Actually, conventional material convex lens, that is converging, that is having converging effect, whereas concave lens, that is having diverging effect. But if the lens is made up of metamaterial, then that effect is interchanged. For example, you can see here a LH convex lens is diverging, whereas RH convex lens is converging. So that focusing nature is interchanged. This is also due to that metamaterial property only. So this is also another interesting thing about a metamaterial. So almost we have covered, we have seen what is metamaterial, what are the properties of metamaterial, what are the two basic metamaterial structures, then what about the transmission line model of metamaterial, then what are the changes in boundary conditions and Snell's law, right? Next, we are going to see what are the different kind of split ring resonator structures. So it will be useful for the scholars, those who want to do research on MIMO metamaterial inspired antenna. So I would like to introduce different kind of split ring resonator structures. So already I told you split ring resonator consists of two metallic rings, right? Also there is a two splits are there. Here this splits, one split is placed on one that is outer ring, another split is placed on inner ring, right? Also there is a gap between inner and outer ring. See, this split ring resonator is known as edge coupled split ring resonator. Actually this is this is introduced on printed circuit board. Actually both rings are placed on same side of the substrate. So you can call this as edge coupled split ring resonator, right? So also we should know what are the effects of this SRR dimensions on resonance frequency. So you can see what is the effect of split width. If you adjust the split width, then what about the resonance frequency, right? That we should know before designing metamaterial inspired antennas, right? So what is the effect of gap distance? You can see there is a gap between outer and the inner ring, no? So what is the effect of gap distance on resonance frequency and metal width, right? If you add additional capacitor, then what about the resonance frequency? So by tuning these parameters, by changing these parameters, you can tune your MIMO antenna to your desired frequency, right? Also by changing these dimension, you can change, you can improve, you can improve the, you can increase the bandwidth of the MIMO antenna. So that's why here I have included this slide also. So this is the basic metamaterial structure. Already I told you, I mentioned in the definition of metamaterial itself. Actually, that is artificial engineered structure, right? The one by using this kind of structure, you can get this metamaterial property. So this is a particular structure used to display what SNG, MNG property, SNG mu negative property, right? Next, see, this is another important structure, broadside coupled split ring resonator. Actually, BCSR, this is used to overcome the drawbacks of ECSRR. Actually, ECSRR suffers from the drawbacks of cross polarization effect and all. So if you want to overcome the drawbacks of these things, then obviously we have to go for a broadside coupled SRR. So broadside coupled SRR means you can see one ring this is placed on one side of the substrate, whereas another ring, right? Another ring is placed on opposite side, that is back side of the substrate, PCB board, printed circuit board, right? So that's why this particular structure is known as broadside coupled SRR. So if you consider equivalent circuit and the current distribution, voltage distribution, it is going to be same as ECSRR only, right? So this is also another structure. This is known as NBSRR, non-bi-anisotropic split ring resonator. You can see both rings are connected together through small metal strips. So this is also used to overcome the drawbacks of ECSRR. So NBSRR, this structure is also very useful for MIMO metamaterial inspired antenna. So by using NBSRR, you can get very good bandwidth, right? This is double split SRR, right? Instead of previous ECSRR, BCSRR and all having only one split on ring, but if you consider double split SRR, we are having two splits on one ring. Another two splits are placed on next ring. So this arrangement is, this particular structure is known as double split SRR, right? So why we go for double split SRR means here, see here for this double split SRR, here this resonance frequency, this is twice the resonance frequency of ECSRR and NBSRR. So if you want to change your MIMO antenna frequency to higher frequency, means you can increase the number of splits on SRR, right? So this arrangement is this structure is known as double split SRR, right? Here you can see a different configuration: single ring with a single split. Next one is single ring with a double split, single ring with 4 split. Next one is double split SRR. Last one is SRR with 4 cuts. So you should know if we increase number of splits, then what is the effect on resonance frequency and bandwidth. If you increase the number of rings, then what is going to be our bandwidth, that and all we should understand. That's why here I have introduced the different configuration of SRR. So you can, I have highlighted here. As the number of splits in the SRR increases, resonant frequency of the antenna also increases. By adding additional ring, reduces the resonant frequency marginally. So if you want to reduce your MIMO antenna frequency to lower frequency, then you can increase the number of rings, right? Instead of 2 ring resonator, you can go for 3 ring, 4 ring. So like that, by changing, by tuning these dimensions, you can tune your MIMO antenna resonance frequency and bandwidth, right? So this is also well-known structure, spiral resonator. You know what is the structure of spiral resonator. So this is equivalent circuit of spiral resonator. So see, why we go for spiral resonator means, see, spiral resonator is a very good structure for size miniaturization and all. By using the spiral, we can get very good miniaturization rate. Say, if you consider a 2-turn spiral resonator, then its resonance frequency equal to half the resonance frequency of ECSRR and NBSRR. So by using spiral resonator, we can design a very small size MIMO antenna. Here also different spiral resonator with 2-loop, spiral resonator with 8-loop, 2-layer multi-layer spiral resonator, broadside coupled spiral resonator. Here I have compared, I have given this comparison between split ring resonator, double split SRR, then spiral resonator. So from this you can understand spiral. By using spiral you can get a lower resonance. For double split SRR, this is used for a higher frequency application. So SRR, you can see this is between spiral. Its frequency lies between spiral and double split SRR. So based on, depending on your applications, you can choose any one of the configuration. Next, metamaterial structure is already I mentioned. No, this is complementary split ring resonator. This is nothing but dual element of split ring resonator. So dual element means, we know very well what is dual elements. Actually, dual network means we have to replace C by L, L by C, series by parallel, parallel by series. No, same thing. By using that duality concept only, this complementary split ring resonator, this is dual element of split ring resonator. So dual element means, so you have to replace metal by slot. You have to remove that metal portion. Instead of that metal, you have to place slots and split by metal. So this is complementary split ring resonator. You can see 2 slots are there, right? Then slits are placed on opposite sides of the slot. So this is complementary split ring resonator. So by using this particular structure, you can get negative permittivity property, right? This is also very, very useful for design of MIMO based, right? Metamaterial based MIMO antennas, right? So this is open split ring resonator. You can see from the structure itself, you can understand split is placed on same side of the ring. So this is known as open split ring resonator. Next, we should understand what are the different kind of metamaterial loading. In what are the ways we can introduce, we can combine metamaterial with the antenna. That's why here I have introduced this particular slide. So I would like to focus on what are the different types of metamaterial loading. So here you can choose transmission line metamaterial loading, right? Then mu negative metamaterial loading, CSRR loaded antenna, partial metamaterial loading. Also, you can also use metamaterial as substrate for your MIMO antenna design. Even you can use superstrate metamaterial as superstrate for your MIMO antenna design. So we will see one by one. See, this is transmission line metamaterial loading, right? Already I talked about, we have seen what is right-handed transmission line, what is left-handed transmission line, what about its transmission line model, right? Already I told you, right? Only thing is you have to introduce inductive effect, capacitive effect, right? So you can introduce this transmission line model on any kind of planar transmission line. See, we all know very well, microstrip planar transmission line, CPW. So you can introduce this transmission line on any kind of PCB board. So this is transmission line model, that is composite right left handed transmission line model. So see, for microstrip transmission line means you can introduce capacitive effect by by introducing series digital capacitor. For inductive effect, you can use shorted stub inductance. So you can introduce this transmission line metamaterial loading on your antenna design, right? Next, you can also introduce, we can also combine mu negative metamaterial with your patch or monopole antenna, right? So that is also used for design of compact size antenna. So in mu negative metamaterial loading, here this mu negative material, that is split ring resonator, is combined with patch. Then this combination, this starts to radiate at a frequency lower than patch. So by using this combination, you can tune your MIMO antenna to, you can change your MIMO antenna resonance frequency to lower frequency. So you can select this mu negative metamaterial loading also. So split ring resonator, we can, by using split ring resonator, we can achieve miniaturization order of lambda by 20. By using spiral, we can get very good miniaturization, lambda by 60. Also, I have included different SRR configuration. First one is multi-split ring resonator, right? Split ring resonator with many splits, no? Multi split ring resonator. Second one is spiral resonator. Third one is, this arrangement is known as labyrinth resonator. Actually, for if you want to design your MIMO antenna for high frequency microwave application, means you have to select a labyrinth split ring resonator. See, even you can also design electrically small antenna also. That is also possible by using metamaterial structures. So ESA, you can say ESA means electrically small antenna. So its size is very, very small. It is less than lambda by 2. Even you can also design size less than lambda by 4 also. That is also possible with the help of metamaterial structures. So here for ESA antenna, actually some conditions are there for ESA antenna. One is a Ka less than 1, and this is defined by Wheeler, and another definition is given by Chu. This is also Chu definition for electrically small antenna. So if you want to design electrically small antenna for your MIMO application, then you have to check these conditions. Then only we can say this is electrically small antenna. So these are all the conditions for electrically small antenna. Then CSRR loaded antenna. So you can also introduce CSRR on radiating patch or on ground plane. So by using CSRR loaded antenna, you can design a very, very small size antenna. Even you can design beam reconfigurable antenna, frequency reconfigurable antenna. You can integrate these things with your MIMO, right? You can rotate beam direction. Also, you can reconfigure your frequency of operation. Also, you can also change the frequency of operation by using CSR or loaded antenna. Actually, this is all very, very useful for recent 5G application. No? So this is very useful for frequency reconfigurable antenna, beam reconfigurable antenna. Also, here metamaterial can also be used as a substrate, right? Instead of conventional dielectric substrate, you can also use this metamaterial as substrate. See, by using metamaterial substrate, we can achieve very good miniaturization rate. We can reduce that patch dimension to lambda naught by 13. This is very, very good miniaturization rate. See, metamaterial superstrate, this is also used for gain improvement, directivity improvement, efficiency improvement. So instead of conventional superstrate, you can use 2 or 3 layers of metamaterial superstrate. So it can be used for gain improvement, metamaterial improvement, directivity improvement, efficiency improvement. See, for 5G MIMO applications and all, this gain improvement, directivity improvement, that is very, very important thing. So you can also use metamaterial as superstrate for your MIMO applications, right? Next, we will move to what a metamaterial inspired antenna. Then we will concentrate our discussion on metamaterial inspired MIMO antennas. First, you should understand what is metamaterial inspired antennas. That's why here I have included some of our research work on metamaterial inspired antennas. Also, I have included slides for MIMO metamaterial inspired antennas. Actually, metamaterial inspired antennas are very good candidate, very good choice for bandwidth improvement, gain improvement, and also you can design electrically small antenna by using metamaterial inspired structures. Also, you can design multi-band antenna. Actually, this multi-band antenna, this is very, very important concept for recent 5G application. No? So you can also design multi-band antenna by using metamaterial inspired structures. So first one, bandwidth enhancement. We will see how to improve the bandwidth of the antenna right? Without changing any one of the dimension, without changing any shape or size or anything, we can improve the bandwidth by using only metamaterial inspired structures, right? So this is bandwidth improvement by using metamaterial inspired antennas. So for this discussion, I have taken a CPW fed rectangle monopole antenna. So CPW, you know very well, coplanar waveguide fed rectangle monopole antenna, right? So here this is introduced on one dielectric FR4 substrate with a dielectric constant. Here I have given all dimension. I have included all parameters. So this is CPW fed rectangle monopole antenna. Actually, CPW fed monopole antenna. This is a very good choice for many wireless application due to these attractive features, right? One is low profile, wide bandwidth, good impedance matching, omnidirectional radiation pattern, right? Actually, here impedance matching. This is very tedious. This one is very tedious task. If you want to get impedance matching over a broad range of frequency means, you have to change dimension or shape or anything you have to do. But by using metamaterial inspired structures, we can improve the bandwidth without doing any alternation in our monopole antenna, right? So first, let me show what about the characteristics of this antenna without metamaterial structures. Then we will see what about the results of metamaterial loaded antenna. So this is written loss characteristics of monopole antenna without metamaterial structures. So you can see bandwidth is 1.46 gigahertz, right? You can also, this frequency ranges from 3.87 to 5.33, but this is not covering entire WLAN application here. So here we want to improve the bandwidth. That's why here splittering resonator, right? This is introduced on backside of the substrate. So here we have to study written loss characteristics after introducing this metamaterial inspired structure, right? Then now you can see the bandwidth. Now bandwidth is what? This is around 3.76 gigahertz, right? Previously bandwidth is less. After introducing this metamaterial structure, we are able to see this improvement in bandwidth, right? So bandwidth is improved, and also return loss is also good. Resonant frequency, this is around 4.7 gigahertz, right? Also VSWR, we all know very well what about the acceptable VSWR value. So this should be less than 2 over our entire bandwidth of this antenna. So this is our design equation for a splittering resonator. By using these equations, you can find inductance value, capacitance value. Also, you can extract permeability and permittivity, right? Then we have to validate this with the help of splittering resonator characteristics. Also, we have to validate this particular structure is metamaterial structure. So for that, you have to extract permeability characteristics, right? You have to show permeability characteristics, right? You have to see permeability, whether it is positive or negative. Then only we can say this particular structure is splittering resonator structures. That's why here I have included S11 characteristics, S21 characteristics. S11, you know very well what a transmission coefficient, S21 transmission coefficient, right? Whereas S11, that is reflection coefficient, right? I have shown both pass band and stop band. So here from this curve, you can understand this. Here pass band of this SRR, this lies in our antenna's desired frequency band. So this particular SRR, from this study, you can see, you can understand this particular SRR, it can be used for bandwidth improvement. Whereas stop band, this is coming, this is coming below our antenna's desired band, so it will not pass the signal over that frequency range. Here, see, you can use this concept in UWB antenna also. If you want to design MIMO antenna for UWB application, right? You want to notch, you want to stop, avoid some other application, then you can use SRR as notch element for UWB ultra wideband application. So this is also useful for notch function. This is also useful for bandwidth improvement. Actually, this is based on pass band and stop band characteristics. Also here I have extracted permeability. Permeability is negative. So from this you can see this particular structure is SNG MNG material. Then we have to see radiation pattern in E plane and H plane at antenna's resonance. Same thing is simulated and is and I have included here. So this is radiation pattern in E plane. So here you can see some kind of eight shape pattern. Right, so bidirectional radiation pattern, this is observed in E plane, whereas omnidirectional radiation pattern, this is observed in H plane. Then see, before going to fabrication, we have to do some parametric study. We have to find optimum dimensions by doing this parametric study. That's why I have done parametric study on length of split ring resonator. Right, by doing this, we can understand what are the effects. What is the effect of this length on bandwidth and resonance frequency, right? So by doing doing this study, you can select your optimum dimension. Then here I have done split gap. What is the effect of split gap on bandwidth and resonance frequency? So this is our fabricated antenna, right? So you can see this is top side of the antenna, this is bottom side of the antenna, right? So top side, this is CPW fed monopole antenna. Bottom side, this is SRR metamaterial inspired antenna. So I think you are able to understand this. What do you mean by metamaterial inspired antenna? So by introducing metamaterial inspired structure, here we are able to attain this. We are able to improve the bandwidth of the antenna. So this is comparison between this proposed approach and already existing approach. So by using proposed this approach, we are able to attain very good bandwidth improvement. So here summary for this work also I have included. So bandwidth enhancement, this was attained through the use of SRR loaded substrate. Impedance bandwidth also good. So here this proposed antenna, it covers 5 gigahertz WLAN and 5.8 gigahertz RFID application. Next, I want to show this particular design for CSRR inspired antenna, complementary split ring resonator loaded ground plane for simultaneous improvement of antenna performance. So I want to show this design for CSRR loading. So for this discussion, I have considered microstrip antenna. Right, you know what is microstrip antenna. Previous one is CPW fed antenna, coplanar waveguide. This is microstrip based antenna. So this is microstrip patch. This is microstrip feed line. Right, backside I have introduced CSRR on ground plane. Right, you know what is CSRR. Already I introduced what is CSRR. So I have included what about the antenna design. So I have included everything. See this this is designed on FR4 substrate with a dielectric constant 4.4. Right. What about the feeding? What about the CSRR position? I have included all details. Next, we have to study the characteristics without CSRR and with CSRR. Then then only we can understand what are the benefits by introducing, what are the special features of the CSRR loading. That's why here I have included included results for antenna without CSRR, with CSRR. So first one you can see this is without loading. You can see resonance frequency, this is around 2.78. Then second one is CSRR loaded antenna. So after introducing CSRR, you can you can move the frequency to you can move the frequency to lower frequency, right? So if you want to move your MIMO antenna frequency to lower frequency, means you can use CSRR loading. Impedance bandwidth also good. So you can also improve the bandwidth of your MIMO antennas, right? Then parametric study I have done on number of slots of CSRR, length of the CSRR. Already I mentioned before going to fabrication, you have to do parametric study. So from parametric study, we will be able to identify what is the optimum, what are all the optimum dimensions for our antenna, right? That's why this is included here. So this is parametric study on CSRR ring width and slit width. Next, we have to study the surface current distribution also. Actually, I have simulated this antenna by using HFSS software. So this is surface current distribution without CSRR and with CSRR. You can see this blue color representation, this current distribution not good, whereas top red and green and all current distribution is good. So for CSRR loaded ground plane, you can see almost current distribution is good around the CSRR elements, right? This is dimension of the antenna. This is photograph of the this antenna, right? You can see this is top side of the substrate. This is bottom side of the substrate. Actually, this is introduced on printed circuit board. This connector is SMA connector. Also here feeding a quarter wave transformer. This is also used here. This is used to get 50 ohm impedance matching. See, transmission line theory, that lambda G by 4 transmission line we have studied, no? Quarter wave transmission line that is used for good impedance matching, no? That's why here I have introduced quarter wave transmission line here. So this is photograph of this antenna. Next, radiation pattern. We have to check radiation pattern for this antenna. So this is radiation pattern in E plane and H plane. And also gain, you can see gain is also very, very good by using CSRR loading. See, for a MIMO application and all, we have to get a very high gain, no? So by using metamaterial inspired structure, we can get what a very good, very high gain. So this is around 5.9 dBi. So this is comparison between proposed approach and already existing approach. So by using this, we can get a gain of 5.93 dB with very small size. But already existing approach here, the gain is also not good. But here 6 dBi, but size is very high. So this is good approach for gain improvement and all. So conclusion for this work is microstrip antenna with CSRR loaded ground plane improves gain and bandwidth, right? CSRR loaded ground plane provides very good gain, bandwidth also higher than unloaded antenna, right? So next one, I want to show this design for design of compact antenna. Actually, for MIMO applications, for any wireless applications, we have to design what a very, very small size antenna. So metamaterial inspired structures are very good candidate, very good choice for design of MIMO antenna. Design of small size MIMO antennas. That's why I have included this particular work also. So let me explain how to design small size antenna by using metamaterial inspired structure. So this is also CPW fed antenna only, coplanar waveguide fed antenna. Right? See, coplanar waveguide fed antenna means both ground planes are placed on same side of the substrate. So this is left side ground plane, this is right side ground plane. This is CPW feed. Then this is radiating element. This is our radiating element. You can see hexagonal splitting resonator is used as radiating element, right? So here, if you see the dimension of SRR, this is very, very small. That is around 0.2 mm only. So here impedance matching. This is this is a tedious task, right? So we have to get very good impedance matching. So impedance matching, this is not good for conventional feed line, right? That's why I have changed this conventional feed line to meander feed line. So by changing this conventional feed line to meander feed line, here current, it will go through somewhat a lengthy path than this conventional feed line, right? So by changing this electrical length, by increasing electrical length of this field line, we can get very good improvement in very good impedance matching, right? So this is meander CPW FET hexagonal split ring resonator monopole antenna for 5.8 gigahertz RFID application. So this is designed for 5.8 RFID application. This is covering this RF frequency range, right? You can see this is the return loss characteristics of conventional field line and the meandered field line. So by doing this meandered field line, we are able to achieve very good return loss. So this is parametric study on meandered field line and hexagonal SRR parameter, right? Here already I have circulated. I have circulated the slides to your organizers. So all of you try to go through this. So this is surface current distribution of antenna with conventional field line and meander field line. So from this conventional field line, from the surface current distribution, you can see surface current distribution. This is not good for conventional field line. Almost blue color. You are able to see only blue color. Whereas if you take meandered field line, here you are able to see red color and green color. So this representing surface current distribution is good for meander field line, meandered CPW FET hexagonal SRR monopole antenna, right? This is good for this combination, right? You can see the size of this antenna, very small. So by using metamaterial inspired structures, we can design very small. You can see the size is very small. This is one of the important requirement for 5G MIMO applications and all. So I think this will be useful for the design of compact antenna, right? So next E plane and H plane radiation pattern. You can see the radiation pattern. This is bidirectional radiation pattern. This is observed in E plane, whereas omnidirectional radiation pattern, this is observed in H plane. Radiation patterns also good. See, by using compact sites also, we are able to get a very good radiation pattern in E plane and H plane, and also gain is also good. So this is also one of the important requirement for 5G MIMO applications, no? So we can also get a very good gain. So here conclusion summary for this particular design is, say, a novel compact meandered CPW feed with hexagonal SRR monopole antenna. This is designed for 5.8 gigahertz RFID application. So good impedance matching, this is attained by meandered field line, right? Here this covers the frequency range from 5.4 to 6, right? So this is covering RFID application, right? Then due to its compact size and good radiation pattern performance, the proposed antenna could be of wide use in 5.8 gigahertz RFID application, right? Here bandwidth is fractional bandwidth is around 10.34%. Gain is 3.1 dBi. Even though size is very small, we are able to achieve good gain. Here size reduction was achieved by employing meandered CPW field line and hexagonal SRR radiating element. Next, we are coming to MIMO Metamaterial inspired antennas. Almost I have introduced metamaterial inspired antenna. What is the need of metamaterial inspired structures? Why we go for metamaterial inspired antenna? Already I mentioned that is used for bandwidth improvement, gain improvement, size miniaturization, and also that is used for design of multi-band antenna. Next, we are moving to design of MIMO antenna, MIMO metamaterial inspired antenna. So next we are going to see our work on MIMO antenna, right? So miniaturized MIMO antenna with CSRR loaded superstrate for X-band applications, right? We have used CSRR superstrate for this antenna, CSRR loaded superstrate, complementary splitting resonator loaded superstrate, right? Then this is covering X-band applications, right? So for our design, We have taken aperture coupled feeding. Actually, what are the different kind of feeding. See, microstrip feeding, you can use coaxial feeding, you can also use, and also what insect feeding. So different feeding techniques are available. Here we have taken aperture coupled feeding for our MIMO design. Actually, aperture coupled feeding, actually this is used to get very good bandwidth, right? This is used for improvement of bandwidth. You can improve the bandwidth of your MIMO antenna, and also we can also improve the gain of the antenna. That's why we have selected aperture coupled two element metamaterial antenna for this design, right? Let me show the design, right? This is content of this particular design, right? You people, we all know very well what is MIMO, right? Actually, MIMO, it is two or more antennas are used at both source and destination. But this is used at both the transmitter side and also receiver side. So by using MIMO, you can improve the channel capacity with a stable connection with less congestion, right? So for MIMO, we have to check we have to see all, discuss all these parameters. So what are the basic parameters, right? See, for MIMO, here isolation between the elements, that should be high, right? Isolation should be high, and the mutual coupling, that should be less, right? So we have to concentrate how to improve the isolation, how to suppress the mutual coupling between the elements, and also we have to find envelope correlation coefficient, right? ECC, envelope correlation coefficient, right? It should be ideal value, that is 0. It should be less, right? And isolation, and you can also find diversity gain also, right? Actually, so many techniques, so many different techniques proposed for antenna isolation, how to improve the isolation of that antenna, how to improve the isolation between the radiating elements. See, by using MTM inspired structure, we can get a very good isolation. Then by using defected ground structure, by some modification in the ground plane, microstrip ground plane, we can get isolation. Simple ground plane modification, by altering some shape or some changes, you can get good isolation. And by using complementary meander line slots, by using this also we can get we can improve the isolation. Parallel coupled line resonator also you can use, and also you can also use electromagnetic band gap structure also we can use for improvement of isolation, right? So these are the different techniques for improve antenna isolation. See, metamaterial superstrate, actually this metamaterial superstrate suppresses the coupling, mutual coupling, and also helps to improve the isolation between the adjacent antenna radiating elements. That's why here we have selected metamaterial superstrate for isolation improvement and suppressing mutual coupling, right? See, we can also use, see, if you consider conventional thing and all, they are using large superstrate, but by using metamaterial superstrate, we can design thin superstrate, very small size superstrate. So small superstrate, in order to obtain high stable gain with good radiation pattern all over the desired frequency band. So that is the special features of metamaterial superstrate for MIMO design. So this our MIMO antenna, this is used to cover X-band applications. We all know very well what is the frequency range assigned for X-band applications, right? See, this frequency range is specified by IEEE, Institute of Electrical and Electronics Engineers, IEEE. This is from 8 to 12 gigahertz, right? This X band is used for radar application, satellite communication application, and wireless computer network also. So many applications are coming under X band application, this particular frequency range. Also, CUG microwave lab and all, we are using X band components only, no. So for PG labs, we are using S band components. So this is also, you can find X band components in our UG laboratory also, right? So X band is used in radar applications, including continuous wave pulsed radar, single polarization, dual polarization, and synthetic aperture radar, and phase array radar, right? So this is an application for X band, this particular frequency range. That's why we have designed this MIMO for X band application. So already I told you, we have used aperture coupling, aperture coupled MIMO antenna. So first I have to explain what do you mean by aperture coupling. So this slide shows the schematic diagram of aperture coupling, right? Here you can see two substrates, right? Here I have mentioned clearly substrate 1, substrate 2. Actually here radiating element, right? This MTM patch, this is introduced on top side of the substrate. Actually FR4, we have used FR4 substrate for this particular MIMO antenna design. Actually this is single element only, right? Design of schematic diagram for single element only. So the FR4 substrate with a dielectric constant 4.4 and thickness 1.6 mm. So this radiating element, that is MTM patches, metamaterial inspired radiating element is used for this MIMO antenna. So this is introduced on top side of the substrate, right? Next, ground plane, if you are able to see this ground plane, this is introduced on second side of the substrate. So this is introduced on top side of the second substrate, right? Here to aperture, this is aperture is placed on ground plane. So this is used to couple feed line and this radiating element. So this is this arrangement is known as aperture coupled microstrip antenna. Whereas if you consider feed line, here you can see microstrip feed line, this is placed on bottom side of the substrate. Actually, why we have selected this aperture coupled antenna for MIMO design is, see, you can change the this distance between first substrate and second substrate. So by changing this, we can get a very good gain, right? And also we can change, we can improve the bandwidth also, right? So that's why here we have selected this aperture coupled antenna for this MIMO antenna design. And also here two substrates are there. Here radiating element is placed on top side of the substrate. So here we can get a very good isolation between the antenna elements, right? That's why we have selected this particular aperture coupling for our MIMO antenna design. So this slide shows the design steps, right? What are the different iteration in this particular antenna design? So here actually this consists of 5 stages, right? So first one, you can see our design starts with only circular patch antenna. In second one, we have changed circular patch to this slots loaded antenna. We have introduced the slots on patch, right? Then we have changed this slots loaded antenna to NB-CSRR loaded antenna. Already I told you what is NB-CSRR, that structure, right? So this is NB-CSRR loaded antenna, right? Next one, we introduced the aperture on first substrate, and also we have introduced this microstrip feed line and bottom of the substrate. So this is the design steps for our MIMO antenna. Then next step, we have introduced one more antenna, one more MIMO element. So actually this is one element only, design steps for one element. In next step, we introduce another next antenna. So this is our proposed antenna, right? Here you can see 2 antennas are there. One is first antenna, right? Metamaterial inspired aperture coupled antenna. This is another second antenna.
between these two antenna, we have introduced array of CSRR also. You are able to see this. I have highlighted here. I'm moving this cursor. You are able to see this. So this array, vertical array, CSRR loaded array. This is also used for mutual coupling suppression. So by introducing this metamaterial inspired structure, we are able to reduce, we are able to suppress mutual coupling between these two radiating elements, right? You are able to see this is two element MIMO antenna, right? This is proposed antenna with two MTM elements with a central CSRR array. So its overall sizes, you can see 30 cross 16 cross 4.7 mm, right? So with this size, we are able to cover that expand application. So this is our final design, two element MIMO antenna for X-band applications, right? Next, see, we have to extract metamaterial characteristics. Then only we can say that particular structure is what a metamaterial structure. That's why here we have extracted NBCSRR characteristics. Right. So this is the design equation for NBCSRR. Actually, NBCSRR, this is used to provide what a negative permittivity. Also, this is coming under our X-band application. So from this study, you can see this particular NBCSRR can be used for generation of resonance around X-band frequency. So I have included all the dimensions of this particular design, right? So this is our fabricated MIMO antenna, right? Two element MIMO antenna. See, we have taken photograph. We have included all. Here we have taken photo along with scale in order to show the size of this antenna first. So from this scale, you can see the size of this antenna. This is very small size. So using with this small size, we are able to cover this X band frequency range for MIMO applications, MIMO antenna, right? So here this first one, actually bottom of the substrate, bottom of the second substrate. So here a microstrip feed is there, right? You can see feed line is introduced on bottom side, whereas aperture, right, two apertures, this is placed on ground plane on the top of the second substrate. We have connected SMA connector. Then this is second substrate. So on the second substrate, we have introduced two MIMO radiating elements, right? So by using NBCSRR radiating element, we can achieve very good bandwidth. Here CSRR also we have introduced between two radiating elements. This is to avoid mutual coupling between the radiating elements, also used to achieve high isolation. So this is our final design, right? So after this fabrication, right, you can take measurement. You can measure S parameters, right? Scattering parameters for these MIMO antenna. You can check what about S11, S22. Then what about isolation between the elements S21, right? From S11, S21. We can find other parameters. We can find all MIMO parameters also, right? See, by using DNA, we can measure S parameters, right? For radiation pattern measurement and gain measurement. That for that you have to go for an anechoic chamber, right? By using horn antenna also, we can measure what radiation pattern and gain. So this is our fabricated antenna for two element MIMO antenna for X band application. See, already I told you this is aperture coupled antenna, right? Actually, our radiating element is placed over the second substrate. So there is some air gap between. Let me show the design. So that you'll be see, you can see here some air gap between second substrate and first substrate. So by changing this gap, right, by changing this gap, you can tune your antenna to decide frequency band, decide frequency, resonance frequency. Also, you can tune your antenna to improve the gain, right? So that's why here we have done return loss study for this particular parameter, right? So simulated return loss variation with frequency for various values of air gap, right? So we have done this study from these parameters from 0 mm to 3 mm. So we are able to find what very good resonance and return loss for this air gate height of 1.5 mm. So based on this study, you can select the dimensions. Then we have done the study for different values of stub length, right? So from this graph, you can see for 4 mm, we are able to achieve very good return loss. Next, we have done the study for different dimensions of this aperture length, right? Already I have shown no where is that aperture, that and also we have done the study for different values of aperture length. So based on this, you can select optimum dimension. And also here we have done the study for gain also. Actually, we have to get a very good gain for MIMO antenna, right? And this is one of the important requirements for MIMO antenna for recent latest wireless applications, right? That's why here we have done this study for different iterations. Actually, I have shown different iterations. So we have compared this gain for different stages. Actually, for antenna last stage, we are getting very good gain. That is for MIMO antenna. Too for antenna D, that is nothing but single element antenna. Antenna E, that is MIMO antenna. So we are getting very good gain for this 2 element MIMO antenna. You can see the gain is around 8.51 dB. So that also we have checked, we have simulated this characteristics also. And also efficiency, we have to check efficiency also. That's why we have done this simulation also. If you see the efficiency, this is around 84.14%. And also you can find envelope correlation coefficient. This is also one of the important parameter for MIMO. So from this ECC, you can understand isolation. So isolation, this is an important parameter of MIMO antenna, which can be measured from ECC value, envelope correlation coefficient value. So you can find ECC from S11, S12, S21, S22. So this is the formula for ECC. So using this, you can find the envelope correlation coefficient. That's why here we have simulated, we have measured ECC value. So you can see measured ECC value, that is around 0.03, right? So ECC, this is very, very less. So this is one of the important requirement for MIMO antenna. ECC should be low, should be less, right? Same thing we are able to achieve by doing metamaterial inspired structures. Then we have to see the radiation pattern in E plane and H plane. Actually, we have to get a stable radiation pattern in E plane and H plane. That's why we have simulated a far field radiation pattern in E plane and H plane. Then we have to show, we have to compare this with already existing work. That's why we have done this comparison also. So we have done this comparison with already existing work. This is comparison in terms of isolation, gain, and efficiency. Here, last one is this approach. So we are able to achieve very good isolation, right? 47 dB, and also gain is also good. Efficiency also good, right? So this is comparison between this approach and previous approach. So conclusion is, so MTM MIMO antenna, it has been designed and implemented to improve the isolation between two NBCSR elements, right? So from this study, you can clearly understand this. So MTM inspired antennas are used for improvement of isolation that is used to get high isolation between two radiating element. And also we have placed the CSRR array, no? So that is also that is also useful for mutual coupling reduction, mutual suppression of mutual coupling, right? So mutual coupling suppression procedures in most of the other technique, most of the existing system, actually that leads to reduction in bandwidth, right? If you introduce some mutual coupling technique, right, other technique, if you consider other technique, that leads to reduction in bandwidth. But here by using this metamaterial inspired structure, we are able to achieve mutual coupling. We are able to suppress mutual coupling without change in bandwidth. And also this antenna, this is low profile, size is very low, no, low profile, and provides better efficiency and gain. And isolation, measured isolation, that is around 47 dB, right? Then this measured frequency ranges, that is from 7.525 gigahertz to 9.1. So this is suitable for X-band military applications. So almost I have included all references. This is our papers on MIMO metamaterial inspired antennas, right? Also I have referred this textbook, last one, and this is metamaterial textbook. I have taken metamaterial contents, basics of metamaterials from these papers. And also this is one of our scholar work, MIMO, miniaturized MIMO antenna with CSR loaded superstrate for X-band application. I have explained this design also. This was accepted for this wireless personal communications, right? I think I hope you all understood what is metamaterial, what is metamaterial inspired antennas, what are the features of metamaterial inspired antennas, right? How it is useful for MIMO design. Also, I have explained one of our research work on MIMO antennas also. Thank you. Thanks for your patience listening. Now you can, if you have any doubt, you can.
Thank you, ma'am. Thank you for your wonderful session. Dear participants, if you have any queries, you can raise your queries to ma'am. You can clarify your doubts. No.
Participants, any doubts?
No queries? If you have any queries, you can ask. Good afternoon, everyone. Good afternoon, everyone. The presentation was extremely informative and speckled with useful words of rich research experience and wisdom. It's definitely going to be useful for all, especially for those who do their research in MIMO antenna design for 5G communication. Thank you, ma'am, for your valuable presentation. Also, I thank all the participants who contributed to the success of this event. So, dear participants, feedback link is shared in the chat box. Kindly submit the feedback form for the attendance and feedback. So next session will start shortly by 2:15 p.m. So topic is artificial intelligence based estimation and prediction method for 5G wireless communication by the resource person, Professor Dr. Ghanshyam Singh from University of Johannesburg, South Africa. So kindly join the link by 2:10 p.m. So once again, thank you all.
Ma'am? Hello, ma'am. Ma'am, one question is there from Mr. Vijay Selvan. What is the coverage of this kinds of antennas, MIMO antennas?
Whether he's asking about frequency bandwidth or frequency range?
Yes, ma'am.
That is X band only, no? I told no. That is covering X band applications. Coverage, that is also good. I have shown no. He's asking about no coverage distance. Oh, okay, he's asking in terms of distance. That we have not checked. Anyway, gain is good, no. So gain is also good. Efficiency also good. So coverage will be good. Coverage distance, that will be good. Shall we use in mobile notes? Yes, definitely we can use it. Okay, thank you all. Thank you very much. Also, my best wishes and congratulations to organizers, Dr. Ponlada and all organizers. Very good arrangement. My congratulations and best wishes to all organizers and also all participants. Thank you very much. Thank you all.
Thanks a lot, ma'am. Thanks a lot for your valuable suggestions as well as for your valuable presentation, ma'am. Thank you, ma'am.
Okay, thank you. Let me, shall I disconnect Dr. Ponlada?
Yes, ma'am.
Thank you. Okay, thank you.
Dear participants, please fill up the feedback form available in the chat box. It is the attendance as well as the feedback form. I request the participants to rejoin for the next session by 2:10 p.m. itself, and I will start the session exactly by 2:15. Thank you.